AC analysis, introduction to AC and resonance. We are coming to another important part of the networks. In this slot we have so many topics. This is called AC analysis. For example, we studied introduction to networks. Part 2 is general analysis technique. Part 3 specific analysis technique. Part 4 transient analysis. This is part 5 AC analysis. In this we have mainly 5 topics: introduction to AC analysis, resonance, phasor analysis, sinusoidal steady state analysis, then finally coupled circuits. These are the 5 topics that we have in this AC analysis. Of course, filters is also there, but filters is for EEE. EC people do not have that, but it's good for EC people also to study, because some public sector exams they are asking even for EC, but for GATE exam filters is not there for EC. That's why I have taken this 5. We'll study that as a separate topic, which is useful for GATE, EEE, and for public sector for all 3 branches, EC, EEE, and instrumentation. So that's our target of this lecture, and target group are those branches. Now let's see the introduction. In introduction, the first thing is rectangular form. For example, if there is an impedance called R plus JX, R is a real part, X is a reactance part, and if the reactance is due to inductor j omega L, due to capacitive 1 by j omega C. So this is reactance of inductor and capacitor. Any circuit consists of both reactive elements, then the resultant should be taken. The resultant is taken as XL and XC difference. This is not minus, this is difference. Why do I say difference? Sometimes XL may be higher, sometimes XC may be higher, but it is the resultant is difference of those two. That's the small idea about rectangular form. Then coming to polar form, an impedance is Z angle theta, where small z is an amplitude, theta is a phase angle. In the rectangle form, we can convert into polar form. Take your Z is equal to RJX, Z is Z angle theta. That means R is equal to Z cos theta, X is Z sin theta. The small z is root of x square plus y square. Theta is tan inverse of x by r. Tan inverse of real term by imaginary term by real term you have to take. For any tan is opposite by adjacent. That conversion you can take. Then operations. Suppose you have addition. How do you add them? Subtraction. Addition, subtraction is done in real rectangle form. Multiplication and division is done in polar form. When you say Z1 plus Z2, X1 plus X2, JY1 and Y2. If you multiply R1, R2, angle theta 1 plus theta 2. If you divide R1 by R2, angle theta 1 minus theta 2. So please follow these notations as we are going to analyze in AC analysis. In fact, I gave this small introduction of AC at the beginning itself. Why? In every topic we have studied AC. That's why I gave a small introduction there. But now it is purely AC analysis. Then, one important point. I have given the conversions for rectangle to polar, polar to rectangle. The reality is you don't need to do like what equations I gave. You can directly use your calculator. In calculator you have rectangle to polar and polar to rectangle. This is what we have. So you don't need to calculate manually. Calculator itself will give you direct answer. So you make use of that facility that are there already in calculator, and you can make things very, very fast in the exam. Now AC sources. AC sources are given by sinusoidal symbol. This is current source, voltage source here, current source here. Magnitude, angle, magnitude, angle. Remember, we will always say Vm cos omega t plus theta. Here, Vm angle theta is one way of representation. Vm cos is another way of representation. So when the frequency is required, they will give frequency. If frequency is not required, you can convert into polar form. So a given trigonometric equation, you can put in the polar form. That's a small idea about AC sources. Note, very important note I have made. In all AC circuits, operating frequency is same because the electric circuits are linear. When the circuit is linear, frequency will never change. So remember, this is a very important precaution. Then what are we going to do in all these calculations and analysis? If the frequency is same, you are only going to calculate magnitude and phase. Input magnitude, output magnitude is going to be different. Input phase and output phase are going to be different because only one thing is going to be same is frequency. That's why that's a very important note, important observation. Then as the frequency is fixed, we are going to calculate magnitude and phase angle. After calculating the magnitude and phase angle, the response should be in the form of excitation. What do I mean by this third point? If the excitation is given in terms of sine, it should be, the response also should be in terms of sine. If it is given in the form of polar form, it should be in the polar form. So before you conclude the answer, you always say put the answer in terms of the input. Calculate the amplitude, calculate the phase angle, then adjust the answer in the form of the input. These are the three important precautions you need to follow as a custom, as a necessary in order to do the better calculations and better answers. So this is small introduction to AC. Then I am going to take you to resonance circuits. Please understand, in transients we have seen the great application called switching. In AC we are seeing another application, very important application called resonance. The word resonance means two things are in line. It's very interesting. This word resonance is not from electrical circuits or engineering. It is there in sound also. It is there in physics. The word resonance was started in intermediate physics or in physics when you have taken a column, air column, and the frequency of the fork, if you hit, the maximum sound come. There are two important things here. There is one thing called natural frequency, another thing called forced frequency. Natural frequency means what is the frequency of the circuit. Forced frequency means what is the frequency you are giving. So what frequency you are giving, if it is equal to the frequency of the circuit, then we say they are in resonance. In sound, maximum sound came. In electrical circuits we call it as maximum current will come. So there are whenever you hear the word resonance in general, either in engineering or in physics or in day-to-day life, it only means one thing: maximum output comes. So for example, here there are two types of resonance circuits. Series resonance circuit, which gives maximum current. Parallel resonance circuit will give maximum impedance. If the word maximum is not there, that's not resonance. I'll give another examples in day-to-day life. When a teacher is teaching and students are listening, there may be 100 students listening, but only few of them understand. And when they understand, their face will glow. that shows maximum smile will come. That means when the teacher is going on teaching at one particular point, student will understand. So when we are talking certain things to people, when they understand, their face will glow. Then we can understand that person is able to understand what we are speaking. So that is called a resonance between student and teacher. So teaching principles has the same. Same thing can occur in any approach, in any relationship. Whenever two people are there, when they understand each other, the maximum glow or maximum smile, maximum you can see the face. So this is basic definition. That's why the resonance we call sound resonance, the resonance between people we call, and finally we are talking about electrical resonance. But remember one thing, maximum current should come. If maximum impedance is coming, in the parallel resonance circuit, when impedance is maximum, current is going to be minimum. So series resonance is generally called resonance. Parallel resonance is called anti-resonance. Why it is called anti? Because the current is less there. So when the current is less, we call it as anti-resonance. So please understand, parallel resonance most of the time elderly people they call it as anti because current is minimum, because it is behaving opposite to resonance. Now let me take you to series resonance circuit. Let us consider a series resonance circuit RLC here. Its impedance is equal to R plus JXL minus XC. Why minus? Because capacitor is minus. Now I am going to make some cases. If XL is lesser, the circuit will become capacitive, negative. If XL is more, capacitive circuit will become positive. Positive means inductive. If both are equal, the circuit becomes resistive because the values will cancel. XL and XC will cancel. It will be purely left as resistive. When it is left as resistive, we call it as resonance. Now calculate. XL is equal to XC. Omega naught L is equal to 1 by omega naught C. Please observe. If you see here, generally we will say omega omega everywhere. But when the resonance occurs, we call it as omega naught. This is one of the important precautions in the entire chapter of resonance. For example, I can say omega L, but I say omega naught because omega L is equal to 1 by omega naught C only at resonance. That's why O for resonance. Then calculate, cross multiply and all that, 1 by root of LC. That's called resonant frequency. This is a very simple way of achieving a resonant frequency. In fact, let them give for any circuit and we are going to have resonance frequency by saying put J term 0. Calculate impedance, put J term 0. That's the simplest way of calculating resonant frequency. Now let me take you to quality factor. This is a very important factor. And one day I was asking, what is the quality of a quality factor? What's the quality? Suppose you have an inductor. Every inductor will have some resistance in general, in series, by mistake. The quality of the inductor is the more energy stored but less dissipation. Suppose an ideal inductor, there is no internal resistance. So the definition is 2 pi into energy stored by energy dissipated. Energy stored should be more if inductor is good. Energy dissipated should be 0. If energy dissipated is 0, that means the resistance is not there, then quality factor is infinity. So quality factor can go even up to infinity ideally. But practically, quality factor is always changing between 10 to 100. It cannot go beyond 100. The whole world is struggling for this. We have seen in resonance the rise time was a very important factor. Here, quality factor is very important. The whole world is stuck up at one word, how to increase the quality factor. If you want to increase the quality factor, the best thing is make a ideal inductor. That's the meaning. So quality factor after calculating will become as 1 by omega RC omega L by R. In general, you can simply say X by R. This equation finalized as reactance by resistance. Okay. So let us use this quality factor in our further discussions. Second point, what is the overall current? Overall current is always voltage by impedance. What is impedance here? Because they are in series, R plus j omega L minus 1 by omega C. Then take R common. If you take R common, 1 j omega L by R 1 by omega C R. That means I am giving another important thing. If this term becomes 0, what happens? I becomes resonant current. So I is equal to V by R if resonance occur. That is called I naught. So I becomes I naught at omega is equal to omega naught. Now I can call this V by R as I naught. So I naught 1 plus j. I am multiplying with omega naught divided with omega naught. Multiply with omega naught divided with omega naught. What can I call this? Please observe. What is this? This is quality factor. Omega L by R is quality factor. 1 by omega CR is also quality factor. So if I take Q as outside, I naught by 1 plus JQ omega by omega naught minus omega naught by omega naught. So this is the expression in terms of quality factor. Now let us define one small fraction. The small fraction means delta omega minus omega naught by omega naught. That means if you subtract this quantity very small by omega naught, so what will happen? Omega by omega naught here minus 1. That means if you bring this one here, delta plus 1 is omega by omega naught. So delta plus 1 is equal to omega by omega naught. We can get I is equal to, look at here, if I put this as 1 plus delta, this is 1 by 1 plus delta. If you take LCM and cancel the small values, delta is very, very small. So finally you will get end up as I is equal to I naught by 1 plus j 2 delta Q. It's good to call as Q naught because it's talking about resonance. So this is all about my second idea to say how to estimate current. Current estimation is done. Third point I am going to talk. Impedance characteristics. What is impedance? Z is equal to R plus j omega L minus 1 by omega C. If you take magnitude, you will get minimum as R. At resonance, as I have been telling, inductor and capacitance they will cancel. Therefore, Z is equal to Z naught. So this is the impedance at resonance. Okay. Similarly, if you take for current, F naught here, this I naught there, I naught by root 2, F1 and F2. These two are done. So this is the magnitude. This is the curve for resonance current. This is the curve for impedance. Both are resonant curves only. One for current, one for. That's why in series current is maximum. Therefore impedance is minimum. Both are not contradicting each other. They are just telling each other. That means supporting each other. Because the impedance is less, current is maximum. Look at there. Then fourth point is bandwidth. Bandwidth is equal to F2 minus F1 radians per second. That's a natural thing. You can call it as radians per second if you say omega 2 minus omega 1. If it is F2 minus F1, you can call it as hertz. So both we will be using, don't get confused. So this is the upper cutoff. This relation between omega naught and F naught and F1 is root of this, root of F1, F2. That's why some people call this F1 and F2 and F naught are in GP. GP means geometrical progression. So it is just like B is equal to root of AC. Similarly, suppose this is A, B, C, B is equal to root of F1, F2. That's another interesting equation. Then if you calculate omega naught by Q, you will get R by L. So please appreciate this value, how much is coming, and the quality factor, omega naught will cancel. What is quality factor? Quality factor is omega L by R. So if omega naught cancel, it becomes simply R by. Please remember, from now onwards, bandwidth wherever I call, I am going to take it as R by L as bandwidth. So R by L is the bandwidth, and you know the omega naught, you know the quality factor. These equations we are going to use in problems. Okay. This is a brief idea about this, what you call bandwidth. Resonant curves. Reactance curves, if I take, let me take negative reactance here, positive reactance there, zero reactance here. How do you understand? XL is omega L. So as frequency increase, XL increase. XC is 1 by omega C. As frequency increase, reactance will decrease. At one point, if you take these two are equal, find out the overall XL minus XC. If I find XL minus XC, you see what's happening. This is the way it's going to. At one point, it becomes 0. That 0 is called resonant frequency. Resonant frequency means inductive reactance and capacitive reactance, totally J term is 0. So from that, you can say wherever you got the frequency at this point, that is called resonant frequency. So this is reactive curves can also help us to know what is happening at the reactance. But remember another thing. If you look at here, look at this curve, overall curve. F less than F naught, capacitive. Capacitive because it is negative. Whenever reactance is negative, we call it as capacitive. When the reactance is positive, we call inductive. So capacitive here, inductive here. Understand? So when you say this is capacitive, I call it as negative phase angle. Negative phase angle means lagging. Similarly, here it is positive phase angle, inductive, and that's called leading. Then what is at resonance over here? At resonance, what's happening is it's becoming 0. Then in other words to say, 0 reactance, that means phase angle is 0. When the phase angle is 0, phi is 0. When the phi is 0, cos phi, which is called power factor, is 1. So in one IAS exam, they were trying to cheat you and check with you whether you know the difference between phase angle and power factor. Wherever the phase angle is 0, please understand the power factor is automatically 0. Power factor becomes unity because phase angle 0. So at the resonance, angle is 0, voltage and current are in phase, but power factor cos phi is unity. So it's not 0 power factor, it is 0 or unity power factor. Let's go to 6th point, relation between bandwidth and damping factor, quality factor F naught. Suppose you know for any second order equation we say S square plus 2 zeta omega n into S omega n square. And what happens is, if you look at here, this is for second order. Then you have S square plus R by L S 1 by LC. Okay. Compare both equations, you can get in the place of omega n you have 1 by LC, that is square, so root comes here. Bandwidth place we have R by L. This already told you R by L is the bandwidth. So looking at the bandwidth, looking at omega n, you can always calculate what you call quality factor also. So these are the relations between bandwidth and F naught. From there others will come. So this is called relation between bandwidth and frequency. Then variation of L and C. Frequency at which inductive voltage becomes maximum, dou VL by dou omega 0. If you do that, 1 by 2 pi root 1 by LC minus R square by 2L. Frequency at which capacitive inductance becomes maximum, dou VC by dou omega 0 here. By this, you can understand, look at the curve please. FC maximum occurs lower than F0. FL maximum occurs higher than F0. By that what I am saying? By that I am saying below F0, as we already decided, F less than F0 it is capacitor and F greater than F0 is inductive. So this is also telling the same point, the maximum occurs only above or below. This is called variation of L and C. That's about variation of L. Now conclusion. F less than F0, X is negative, capacitive, okay, and then F greater than F0 it is inductive, and then resistive it's a unity power factor. Then parallel resonance. Parallel resonance circuit has, let the admittance of the network is this. By the way, why should we go for admittance? We go for admittance for one reason, because they are all in parallel. When things are in parallel, we should always go in admittance. It is easy to add, because in series impedance is added, in parallel what is added? Admittance is added. So we can take the admittance, the overall admittance of resistor 1 by R, admittance of capacitor j omega c minus 1 by omega. So observe this admittance factor. As usual, at resonance what will happen? Anywhere you will have this term 0. So this will be the frequency. Actually, this is approximate frequency. The exact frequency, if you want, the best thing is rationalize this term, and after the rationalization put j term 0. You will get a small change. In that change we can always neglect, because resistance is here. Normally, please look at this circuit. This circuit, RLC circuit, this is not the actual circuit. This is only for analysis. What will be the actual circuit? This resistor will not be outside the inductor. This will be inside the inductor. If you take inside inductor, then analysis will become slightly modified. So please remember, this is for all the three in parallel. Otherwise, if it is here, it becomes slightly changed. Now, which one is practical? This is theoretical, but if you put this resistor inside the inductor, that becomes practical circuit. That's called parallel resonant practical circuit. Let's go to the quality factor as we started in series. So definition is same, energy stored by energy dissipated. Then there and here the difference, that was 1 by omega CR, omega L by R. It is opposite here. Parallel and series almost opposite. Okay. Second, voltage and admittance responses. Admittance, as I told you, if you want magnitude, root of 1 by R square, 1 by omega L, omega C whole square. So calculate here. Same thing you can calculate. Whatever you got for I, you will get for Z. Impedance you can calculate. Bandwidth also same formulas. F0 is root of F1 to whole square. Quality factor we already studied. The only thing you must understand, bandwidth is resonant frequency by quality factor. This is 1 by RC, that is L by R, R by L. So in series it was R by L, now it is 1 by RC. So look at that change from the previous one to this. Then reactive curves. Please observe, in series this was XC, this was XL, but now it is opposite. Then the overall will become again capacitive here, that means lagging, inductive here, that means leading. So lagging, leading phase angles will be there. So this is just a series, same as previous one, only changes XL becomes XC, that's all. Relation also same. As I told you, there it was R by L, now it is 1 by RC. Bandwidth is 1 by RC. Frequency is anyway 1 by root of LC. So these two are very important for our calculations. Zeta, the damping factor is after all an intermediate step for calculation. But ultimate steps are what is the frequency, what is the bandwidth. Now we'll go for variation in L and C. How to vary this one, L and C. Just like previous, what is F1, what is F2? 1 minus zeta, that's why F1 is less than F0. F2 is more than F0. You see there, F2 is more than F0, F1 is less than. This was actually called in the series, this is called VC, now it is IL. This was VL inductor, now it is IC. The actual one is IR. So these are the variations and the curves that we have. Conclusions. F greater than F0. And when you see there, if you see the curves here, I'll show once again. F greater than F0, it is due to capacitance. But what is happening? It is finally leading. This is due to inductor, but finally lagging. So remember these two curves. What is finally happening? So F greater than F0, it is positive. F less than F0, it is negative. So this is what I mean. You need to continue. Relation between series and parallel circuits. The equivalent characteristic equation, you will get it as this is series. As I told you, there are two parallel circuits. One is LC, where R is in series with inductor. In our basic study, we have taken this R also in parallel. So now I am going to give a very interesting conclusion, because this is more of practical, whereas the previous is theoretical, because nobody will connect a resistor in series. Even in series resonance, please understand, it is R is always part of L. Only for our theoretical analysis we took it outside. Otherwise, nobody will connect a resistor separately. Resistor is always in series with inductor. Suppose you have this and calculate the impedance of this circuit and equate with parallel. This is the parallel. I am calling as RP, LP, CP. The previous I have called as LS, RS, CS. If you calculate the impedances and equate them, you will get the answer. LP is equal to LS, CP is equal to CS. Only one thing will change, RP. RP is RS into Q square. Therefore, except this small change, RP, RS into Q square, all others are same. So whenever the question paper comes, or in engineering and industry also, when there is all three in parallel, you can convert them into series. Series you can convert them into parallel. So conversion is possible in this way. With this understanding, I can take RLC circuit as a parallel like this, or RLC circuit as serial like this. So whether the examiner is coming in serially or parallelly, you can convert them and bring this into this form. With this form, you can really get our analysis tuned, because all that analysis I have done with this circuit, if I convert the series circuit into this one, you can easily go with the same answer. So you must be always aware of the small change that is happening. Now we'll go to problems there. The problems, we'll see one by one how the theoretical concept that we studied are useful here. There are so many problems in resonance because there will be no question paper without resonance. So please follow and see. So let me give one by one. Problem 1, right? In a series RLC circuit, quality factor is 100. F0 is 1 kilo. If all the elements are doubled, and then the new quality factor is, what is the quality factor? Is it modified or same? Options are given 25, 50, 100, as if the options are each one is multiplied with 2. You can understand with your aptitude logic. Now what is the answer? Answer is very simple. Obtain the quality factor in terms of your RLC components. As I told you already, F0 is 1 by 2 pi root LC. Okay. Then bandwidth is R by L. So what is quality factor? With that we can see the solution here. Omega naught is 1 by root LC. Therefore quality factor is omega naught L by R. So if the quality factor 1 is 1 by R root of L by C, then what should be the quality factor of 2? All are double. What do you mean by double? Resistor is double, inductor is double, capacitor is double. This 2 and this 2 will cancel. Then you bring it this to half. So this becomes half of the previous. Half of the previous means half of 100 is 50. It's a very simple equation. So be aware of these equations. And the equation is omega naught 1 by root LC. Bandwidth is R by L. And bandwidth is equal to F0 by Q. So Q is equal to F0 by bandwidth. So this is how we can get this bandwidth equation and convert this into here. So this is how you can get the answer as B. Now let's go for the second problem. Transfer function is given 10 power 6 by s square plus 20s plus 10 power 6. Then calculate omega naught and quality factor. These are the options given. What is our standard equation? Our standard equation is s square plus r by l into s1 by lc. So what is r by l? Generally bandwidth, that is 20. 1 by lc 10 power 6. If you compare this standard equation in terms of the values given for bandwidth and 1 by lc, finally what will be the omega naught? 1 by root lc. So if 1 by lc is here, 10 power 3 is here, quality factor will become 50. Third problem. For what value of omega the circuit shown in figure becomes resonance? For what value of omega the circuit becomes resonance? Please remember, let them give any circuit. You simply calculate impedance. Put J term 0. If you put J term 0, the resonance will automatically come. So let us see. ZL is j omega L plus R plus 1 by j omega C. Okay. This is nothing but parallel combination of these two. If you rationalize and finish, finally what is the J term here? Take the J term 0. What are the J terms you have in this? Then you will get omega is equal to 1 by root of LC R square C square. So standard procedure, let them give any circuit. For example, this circuit R plus 1 by j omega C in parallel with j omega L. This is how you have to calculate resonance. So let them give tomorrow any circuit which you have never seen in the exam, never seen in the studies preparation. Let them give in the exam. You don't be panic. Simple, calculate impedance or admittance. Put J term 0. Sometimes if required, take rationalization, because keeping j term 0, you should convert the total function as real part plus imaginary part. If you say real part and imaginary part and put imaginary part 0, you will get the frequency. That is the very important standard procedure for resonance. Then, the resonant frequency, if the resonant circuit shown in figure, what is this here? Suddenly, coupled circuit came. Let me tell you one thing. Coupled circuit, if this dot is entering, this dot is leaving, they are opposite. Opposite means you have to calculate the effective inductance 2 Henries from here and what is subtracted. So because one is entering, other is leaving, it is opposite. Now you see what I am going to do there. L equivalent is equal to L1 plus L2 minus 2M. 4 minus 2 into. This is becoming 2 Henries. So effective inductance is 2 Henries and capacitance anyway you saw there as 2. So what is the answer then? F is equal to 1 by 2. Pi means 3.14. Root of LC. L is 2, C is 2, 4. Root of 4 means 2. So this is simply 1 by 4 pi. 1 by 4 pi means the option is B there. So this idea is only to tell you how to use the coupling concept in the resonance. And I like this word, the circuit, very much because you look at here, there is no resonance here. There is no resistance here. Please remember, ideally speaking, there would be no resistance as far as your inductance is concerned. So he is taking ideal inductances. That's why there is no resistive component. This is, I call this as series LC circuit without resistance at all. So this is the GATE problem given to you, and that's for 2 marks. It's very interesting. Maybe he has given 2 marks because coupling concept is here. Most of the students will leave this problem. If the coupling concept is there, everybody becomes panic and leave it. That's why maybe he gave it 2. It's the worth of 2, though the problem seems to be simple, but the concept of coupling is involved. Okay, that's the solution. Now, 5th problem. In a series RLC high Q circuit, the current peaks at a frequency. At what current is becoming peak? The answer is equal to resonance frequency, greater than the resonance, less than the resonance, none of the above. Very simple. Please remember, the maximum comes only when the resonance is there, because greater than resonance means F2, less than resonance means F1. At F1 and F2 it is I by root 2. So what is the maximum value occurs at resonance frequencies. Therefore option is A. Now very practical problem. A series RLC circuit consisting of 10 ohms, XL is 20, XC is 20, connected across AC supply. How are these 3 elements connected? Serially. The voltage given is 200. The RMS voltage across the capacitor, what is this value? This is the question given in ECE. Such a big question for only 1 mark? Yes. Because there is nothing difficult here. Look at this. Suppose you have a RLC component connected in series. What is the current at resonance? At resonance, generally what will happen? Inductive current, capacitive, they cancel. You will have only resistor. So voltage is 200, resistance is 10. Therefore the current flowing in the circuit is 20. So voltage across capacitor is how much? Very simply 20 into 1 by j omega c. 1 by j omega c is already given as this. So you can substitute 20 into minus j omega c. Then he himself gave this is 20 in the question. 20 into 20 becomes 400 minus j 400. If you convert this minus j 400 into polar form, 400 is here, minus j means minus 90. So the option is D, 400 minus. So you have calculated the actual current. In that current, how much is serially going? The same current is going through this serial, and suddenly calculate across the voltage across the capacitor. They're very simply speaking, same current everywhere, current into impedance. Current is to 1 by j omega c is impedance. Even that frequency is, you don't need to calculate that minus 20. This minus j20 you don't need to calculate. In fact, you cannot, because the frequency is not mentioned. When the frequency is not mentioned, he has every obligation to give us the value. And he gave the value, so 20 into minus j20 minus j400. Okay. So this is how you have to calculate the thing. Question number 7. Problem number 7. We don't call problems in GATE, we only call as questions. A series RLC circuit has a quality factor of 100 and an impedance of 100 plus J0. Please observe that. J0 means it's purely impedance. At its resonance angular frequency of 10 power 7, natural. At resonance, the impedance will be 0. He is asking us the value of L. What is the value of inductor? So how do you think we are going to attack this problem? The answer is simple. Quality factor you get in terms of L. And in that, quality factor is given, resistance is given, only unknown is L. So please observe this. He has given the values 1, 2, 3, 4 millihenries. Now, quality factor is omega L by R. That's a very standard value. Quality factor is omega L by R is a standard value, and he has given 100 here. Omega is 10 power 7. L we don't know. R is given. So if you cross multiply or take this value, you will get this as 1 into millihenries. 1 millihenries is the answer. The option is A. 8th question. In a series RLC circuit, resistor is 2 kilo ohms, L is 1 Henry, capacitance is 1 by 400 micro. Then the resonant frequency, one mark here given to you. So what is the frequency? Answer is very simple. If you want the frequency, answer is simple, 1 by 2 pi root LC. So simple. You don't need to calculate and use the value of resistance there. 1 by 2 pi root LC. 1 by 2 pi root 1 into 10 power 6, 1 by 400. And if you see this 1 Henry, why should I multiply with 10 power 6? Because 400 micro, this becomes 10 power minus 6 goes and become 10 power plus 6. So answer is, if you calculate, just 2 zeros will cancel. So 4 10 power 4. This 10 power 4 will be here, and this 2 zeros also come up there, and 2 and 4 will be cancelling under root. So you will have 10 power 6 means another 2, 10 power 8. Root of 10 power 8 how much? 10 power 4. So that's why 10 power 4 by pi. You see, examiner is not asking you to calculate the actual value. As you saw, most of the questions he gave in terms of pi. In terms of pi. Good. So the option is C here. 9th one. The following circuit shown in the figure, the resonant frequency we have to calculate. Will it resonate at all frequencies? 0.5 radians per second or 5 radians per second, 1 radians per second, 10, 4, 1 farad, 1 farad. This is what we have. As I told you, for any resonant circuit, we will calculate impedance, put J term 0. Shall we do that? Let's see. Before even I go further, I'll just help you see this j omega L, 1 by j omega C, 1 by j omega C. Take the parallel of this. So 1 by j omega C parallel, j omega L plus 1 by j omega C. All that put together in series with 10. Shall we do that? Look at here, as I told you, 10 j omega minus 1 by in parallel with this. If you convert and rationalize this term, you will get here. As I told you, any resonant frequency will come when you say at resonance j term is 0. If this will become 4 omega minus 2 omega becomes 0. Therefore, 4 is equal to 1 by omega square. 4 is equal to 1 by omega square means how much? Omega square is 1 by 4. Therefore, omega is root of 1 by 4. That means 1 by 2. 1 by 2 means how much? 0.5 radians per second. So 0.5 radians per second is the value here. Question number 10. A series resonant circuit has following parameters. Resistance is 10 ohms, inductance is 0.01 henries, capacitance is 100 millifarads. Then quality factor at resonance condition should be. This is the quality factor value is given. Look at the answer. Quality factor is 1 by R root L by C. You can take another equation, that is omega L by R. So when omega is given, that's the equation. If omega is not there, substitute omega as 1 by root LC, get this equation. Substitute 1 by R root of 0.01, 0.1. How come this 0.01? Okay. Because he gave the values. Inductance 0.01. Capacitance is 100 into 10 power minus 3. 100 into 10 power minus 3 is 0.1. That's why this is the answer, 0.0316. Therefore, the option is A. Question number 11. A circuit with RLC in series is resonant at F0. If all the component values are now doubled, then the new resonant frequency will be this. See, the same question was asked, all the components are doubled in the previous. That was for quality factor. Now it is for F0. F0 is independent of resistor. So, when you say resonant frequency is 1 by root LC, if all the components are doubled, what will happen? L is double, C is double, it becomes 4. Root of 4 means 1 by 2. So, F0 by 2. So, F0 by 2 means what? The option is C, because look at here, he is asking in terms of C only, in terms of F0 only. He is not giving the values. So, F0 by 2. Normally, people expect that 2 into 2 becomes 4 F0 by 4, but they forget root. That's why F0 by 2 is the answer. 12th one. The current in the circuit shown in figure, what should be the current? This is 200, this is 200. This is plus minus. Please observe, inductor is positive, capacitor is negative. Positive is 200, this is negative 200, they get cancelled. Therefore, the total has to go with the resistor. If the total is going with resistor, what will happen? 100 volts by 20 will become 5. And this is the option A. Very simple. Directly at resonance, as we studied in theory concept, these two get cancelled. These two are equal. Understand? No further concept is there. Now, problem number 13. The circuit shown in figure, what value of C cause a unity power factor at the AC source? What value of C cause a unity power factor? So look at this. He is asking for what value of C. This is more practical in the industry. You know why? Because this is coil available the value is 30 angle 40. And you need some other angle, for example, angle should be neutralized. Okay. If you neutralize the angle, what will happen? That is in resonance. So definitely we understand there is a positive angle given here. You need a capacitor. Even if it doesn't say capacitor, I would put capacitor, because to neutralize positive angle we need a negative angle. That's everything by concept. So what best you can do is you call this as a circuit, calculate impedance, put J term 0, because unity power factor means phase angle is 0. Phase angle is 0 means resonance. Put J term 0, you will finish up the answer. So look at here. So equivalent impedance, this is in parallel, no, I am taking it as admittance. If I take admittance, j omega c plus 1 by j omega L, 1 by 30 into 40. Now you convert this and j omega c here. This one is already a real value, this is imaginary value. Now what to do? Put j term 0. That means omega c minus 0.241. What will happen? If you calculate this, you will get c as 68.1 micro. What an interesting thing. For example, because of this phase angle, if any industry or the work in industry is stuck up, you just insert a capacitor and make the work done. Suppose if the capacitor is not there, maximum current is not coming, or maximum impedance is not coming, the whole purpose is lost. By just inserting one capacitor, you have solved the problem. So it's not only to say capacitor has to be included, it is also to say the value of the capacitor. Option is A. Question number 14. In the circuit of figure, the magnitude of VL and VC are twice that of VR. Given that frequency is of 50 Hz, the inductance of the coil should be. Oh, very good. The answer is very simple. Look at this. He gave VR. Okay. He said this is equal to twice. So VL is equal to 2 times of VR. VC is equal to 2 times of VR. They are the 2 times of VR. And you know one thing, in resonance or at resonance, these two will cancel. When these two are cancelled, okay, you can easily calculate the current. Calculate the current as phi angle 0 by phi angle 0, 1 ampere. If this is current is 1 ampere, 1 ampere into 5 will become 5 volts. If this is 5 volts, he is asking for the inductance, then I would say if this is 5 volts, inductance should be how much? Twice of 5, 10. But from 10 you can calculate omega L is equal to 10. Calculate L. That's what the solution going to be. Option is C. Look at here, 2 times, as I told you, it is 2 times, and you can say omega L. Even without calculating quality factor, you can calculate this. So omega L is equal to, see here, that's what exactly I did. Can you look at here? L is equal to 10 by omega. And omega is what? 3.14 into, what's the frequency he gave? 50. So if you calculate that way, so apply this KVL, VR plus JL and all that, and resonance means this should be 0. Then as I told you, the quality factor is VL by VR, omega L by R, omega cancel, that is 2. So quality factor is 2 means what? 2 is equal to omega L by R. Calculate this. This is what we mean. The option is here. So we are calculating quality factor from this, because he said it is double. VL by VR is equal to 2, that is equal to quality factor. Omega L you calculate by 5. Calculate this. Inductance will come. Question number 15. The value of Z in figure, which is most appropriate to cause parallel resonance at 500. Again, same question just like in the previous questions. Capacitance we calculated, we have to calculate Z now. So my argument is very simple again. Calculate impedance, put J term 0, equate that frequency to 500, you will calculate Z. So that is a very simple thought. That's why it's only a calculation involved, no new concept is involved here. Now let me give you the solution. What is the equivalent admittance? 1 by R, 1 by j omega. This simply I don't know what is that value. We just say Z whatever it is. Why? Because it's unknown. We need to calculate. For resonance condition, what should happen? This should become, reactant terms should become 0. And if this reactant term is 0, minus j1 by omega L, j omega C should be 0. Just like in the previous question, if you calculate this one, you know L, you only need to know C. So in any question, it's a very standard thing. Calculate J term and put that J term to 0. You may get the frequency there, you may get the L there, you may get C. Okay. So this is how he is asking you different ways of calculating what you call unknown element. Whenever we are calculating unknown element, understand this is unknown element is nothing but design. So all that we are doing, if the component values are known, it is called analysis. If the component value is estimated, it is called design. So we are also designing certain circuits to give us the actual values and to see that the circuit will work. So therefore the option is D. Out of all the values given, option is D there. Now 16. Resonant frequency for the circuit shown. Oh, what a simple circuit. Please understand why I am taking so many circuits, or why examiner is asking so many circuits. I have not taken not much of my own. I am actually keeping all the examination questions, because certain questions which are not there I may put myself, but most of them are previous exam papers. Because he already gave it, I am only taking them into sequence. I am not going year wise sequence, I am going concept based sequence. So therefore, now if you look at this circuit, what are the varieties of circuits we are talking? Look at that. See, there are basically two circuits, series resonance, parallel resonance. Series resonance means standard circuit. Parallel resonance also standard circuit. But you can have any circuit of your choice or the choice of the application. So this is what is this circuit actually? Is it serial or parallel? The answer is it's neither series nor parallel. So just for study, we have studied serial and parallel. They are given you two standard circuits and their analysis, and more than that, they have given you the analysis approach for circuits. When the analysis approach for circuit is given, this is the new circuit. So let them give any circuit we have or we want and do this. For example, now what is you calculate impedance here. These two are in parallel plus series with that. This is 1 ohm, 1 by j omega C, means C is 1, j omega L, L is 0.1. So calculate that impedance. For example, j omega L is in serially added, R into 1 by j omega C, R plus n by j omega C. What do I do here? I will be taking, if I multiply this, then real value I will put here, imaginary value I will put inside. So as I have been telling, imaginary value you should always make it as 0. If you make the imaginary value as 0, then 0.1 omega minus omega 1 by omega square is equal to 0. If you equate this term, okay, omega square plus 1 is equal to 10. That means what? Omega square is 9 and root of 9 is plus or minus 3. Another important precaution in the analysis, please. Whenever you say frequency plus or minus 3, omega means radians per second, frequency f means hertz. Whether it is omega or hertz is not the main point. Main point is frequency cannot be negative. In entire analysis of engineering, frequency cannot be negative. So actually in this problem you got omega is plus or minus 3, but we don't take minus 3, we will take only plus 3, because frequency cannot be negative, only positive value is taken. Why frequency cannot be negative? Frequency cannot be negative for one reason. You know what is that? Number of cycles per second cannot be negative, it should be positive value. So remember, frequency can never be negative.